embedding specular highlight into it because I cannot actually see it. Even if I do, then the cone of the specular direction becomes so large that over the region of my camera, my imaging plane, the amount of energy I'm capturing is remaining uniform across that. So really the specularity has been removed. So those are interesting things to keep in mind and sort of take from these models as to what is the true applicability of these models, under what conditions can you apply them when you are trying to recover geometry from it. Now, as I said, we made certain assumptions on the geometry of the image, and if I do not want to ignore the notions or the effect of scattering of light as well as self-shadowing of the object, I have to now again expand my model a little bit further. And one of the approaches to expand that model further is to look at a model that was proposed by Torrance Sparrow, which tried to look at specular reflections in terms of rough surfaces. Right? What happens when I have surfaces that are not truly planar? How is specularity going to get computed for that? An example of that is that imagine that you actually have a surface which does have a lot of variation on it. Amount of light coming onto it is not always going to get fully reflected. In fact, some of it may reflect onto other surfaces itself of the object. And as a result, you may have scattering of that light back onto the object. Right? So what happens in those cases? On a global scale, if you start thinking about it, all of a sudden you've gone from one source of light now to multiple sources of light, because the object itself is illuminating its own surface. Right? So that becomes fairly complicated. More importantly, when we actually look at real scenes, we have to extend this notion to neighboring objects. Right? I may have a certain amount of light because of having a source of illumination. But the source of illumination that I have for imaging a particular object is not going to be that same source all the time. So I have a source, right, it's illuminating this particular object. But portion of the light is actually getting reflected onto the other object. Or for that matter, source of light is also illuminating that object, and portion of the reflected light is illuminating this object. So this object has multiple sources of illumination. So the goal that we have looked at in terms of these basic models do not explain the interaction of multiple objects and the light emitted from there. So if we want to truly model all these properties, how do we go about doing it? It becomes a very, very complex problem. So the Torrance Sparrow model can do some of that, but much more in terms of explaining the microfacet geometry of individual objects. Okay. So first and foremost, what does it try to do? It tries to say that, well, I have, rather than having a single normal for the entire surface, I will represent the surface in terms of microfacet orientation. So I have multiple normals. Now, the amount of roughness that I explain from my surface, I can try to model under some parametric distribution function. And what it actually uses is more of a Gaussian model. So if I want to explain the interaction of, let's say, the surface, which I can truly talk about in terms of its albedo, right, at any given point, the amount of light coming in and the amount of light going out, which is related to the normal in the albedo, right? So I need to define some relationship at every given point on a surface in terms of its normal, its albedo, and of course the source vector. How do I describe it? And you know, the Torrance Sparrow model said, well, let's just capture everything in terms of some isotropic Gaussian model. Right? But I'll do that on a point-wise basis. So we can try to represent that, where now you can express that in terms of a Gaussian model where sigma defines what we call the roughness parameter of my surface. So if you consider a rather peak Gaussian, then you are going to more or less reduce all of this to make it a very, very narrow form. So I can express that as being sort of almost speculative. On the other hand, if I make the Gaussian very wide, I'm sort of going more towards diffuse things. So now if I do this at every point in my model, then I'm playing with the range of diffusivity and specularity as opposed to having this constant terms that I compute over my entire object. And that allows for better explanation of how we think of the surface as being a microfaceted. Okay? So what the model then says is that, well, I will compute the radiance in terms of course, a specular component, and that is normalized by n times v, right, where v is the actual direction of the camera. So that tells me amount of specular energy that's going towards the camera. And then I will modulate everything in terms of my P of D data, right? This is my microfacet geometry that I define. And a geometric factor which is expressing what we consider the masking and shadowing effect that occur because of the microfacet geometry. So in general, there are two main components that happen because of the varied geometry. One, you will get shadows, because a portion of the surface may never get illuminated, depending on the way it's oriented. Or you may get shadows, which is a portion of the surface of the object is actually overshadowing something else. So there's a diminished amount of energy that gets transferred. So all of these we can capture in terms of this generalized geometric factor that is expressed in the model. So this is really the extension in terms of what the Totten-Sparrow model does. It tries to capture this, and this is how we express the true amount of energy that we're going to measure in terms of intensities. Okay? Make sense? Okay. All right. Now, from a vision standpoint, right, we have created, in general, some models, physics-based models, that express the relationship of the energy emitted off of an object based on the surface properties of the object and, of course, the light source. Now, as I said, in reality, this is not sort of a standalone relationship. Right? There are multiple objects that interact and so on and so forth. Furthermore, the light source itself, or the radiosity that we are interested in capturing, may become a property of that object itself. Right? So there's a component that's contributing to the intensity that we observe because of an external light source. And there's another property that we are observing because of the object itself. Now, how do I differentiate the two? One way of doing that is to define a term called exitance. Okay. So exitance is actually the source of illumination that is internally generated. So every object, you can think of it as having its own internal source of light. So that's independent of any other source of light. It's just an exitance term. Okay. And which is somewhat similar to radiosity, if you think of it, because what we want to measure is the intensity of the object, right? And we measure that in terms of radiosity. We simply equate it back to the intensity values. But if I think of the object will have exitance properties because, one, it may be actually getting illuminated by a secondary object, right, that might be reflecting a certain amount of energy onto it. So it may not actually get any energy because of the illuminant source, right, an external illuminant source. It may be getting its full energy simply because there is a neighboring object that's emitting a portion of